Hello, everyone, and welcome to today's webinar, How to Calculate Safety Stock and Evaluate Different Methods Battling the Assumption of Normal Distribution. This is part 3 in a multi-part series. Thanks for taking the time to join us today. I am Kristen Tiley, the Director of Marketing here at Arqiva, and I'm your moderator today. Discussing our topic will be Sujit Singh, COO here at Arqiva. Sujit, can you quickly introduce yourself?
Sure. Hey, thanks, Kristen. So yeah, I've been working on safety stock and associated inventory topics for a long enough time. And people ask questions about why we always use normal distribution in calculating safety stocks. So as we have been doing this series on safety stocks, I'm very pleased to be able to present on this topic today.
Great, thank you. We have a few announcements before we begin. If at any point you have trouble hearing us, please let us know using the chat feature and we'll be sure to assist you. We do also have a couple polling questions in today's session, so we encourage you to respond to those when they come up. And there will be time at the end of the session for questions. You may submit an online question at any time using the questions window. Before I hand it over to Sujit, I'd like to share a little bit about Arqiva. For more than 30 years, Arqiva has helped global enterprises drive business transformation through improved supply chain processes. Recognized by Gartner in the Gartner Supply Chain Planning Solutions Magic Quadrant, everything we do is aimed at solving complex planning challenges and creating cutting-edge technology that enables you to run your business at peak performance. We continually challenge ourselves to create solutions that not only solve today's challenges, but future challenges as well. We live in a dynamic world where speed, accuracy, and efficiency are critical to drive business transformation, and we believe that starts with better planning. Our goal is to enable your business to benefit and thrive from the way our solutions unlock the true value of your supply chain. Our fully integrated S&OP solution is a demand-driven business planning process that promotes cross-functional synchronization within the company, starting from integrated financial planning to demand and inventory management to create a more dynamic management process using real-time dashboards. And with that introduction, I'll hand things over to Sujit.
Thank you, Kristen. All right, so let's look at the agenda real quick. What we'll do is we'll begin with a recap of part 1 and 2. Like I was saying earlier, this is part of a 3-part series that we have put together on safety stocks. So it makes sense to do a quick recap. Then we'll discuss why normal distribution is so popular in general, but also in the world of safety stocks. And then we'll start looking at some alternatives. We'll begin with the special case of Poisson distribution, which does not apply everywhere, but there are certain cases where it works very well. We'll talk about scanning as a method of bypassing normal distribution. And then really we'll spend a bunch of time on bootstrap sampling, which is the technique I'm most interested in talking about as a potential replacement for normal distribution or any kind of assumption of any distribution when it comes to calculating safety stocks. Once we have done that, and by the way, when we do that, we'll really get into the how-to part using Excel as well. But then we'll conclude with some observations, and then that'll be that. So let us jump in. So, and the first thing I want to do is kind of get a sense of how many of you have been following this series. So here we begin with a polling question. Did you watch the first 2 parts of this webinar series? All right, well, looks like majority of you have not watched either. 89% of the votes are for not yet. So that certainly my suggestion would be to do watch that. Certainly, if you are from the world of safety stocks, those 2 follow what is typically discussed in the world of safety stocks. Today's topic is a little bit advanced, and it does use some nomenclature from the previous 2 presentations, but I'll do my best to cover that. But I do recommend that you watch the first 2 parts as well when you can, and feel free to reach out to us if you don't find the link to it. Okay, so quick recap of part 1 and part 2. we went through calculating safety stocks. Both those webinars were titled How to Calculate Safety Stocks. So in that, we considered things like service levels. We talked about the cycle service level versus the volume fill rate service level. As far as the distribution of the data, we just assumed a normal distribution, and we talked about that. So really, it was very unidimensional in that aspect. And then we talked about the different variabilities that lead us to carrying the need for carrying safety stocks, things like variability in the demand, variability in the lead time, variability in the supply quantity. And we incorporated all these different variabilities in the process of calculating safety stocks. And since we assume normal distribution, it followed the very standard formula of Z times square root of this standard deviation of demand. And that Z is a factor that comes from the normal distribution. And as I said, this was discussed in great detail in part 1 and then part 2 as well. So I really cannot go over all of that. But as far as that goes, the assumption being that everything is, all the demand data is normally distributed, the Z factor being pulled up from a normal distribution table made sense. But today we are going to go beyond that. And so first part of that discussion is why people use or love the normal distribution. Why is it so popular? Well, first of all, it's easy to use and explain. If you go to a statistics class, you may never get past the normal distribution or the bell curve, as it's sometimes called. It's relatively easy to explain. The math it's behind it, may look a little bit scary, but just the picture of it and explaining things that things are spread around a particular mean are fairly easy for people to understand. Then the other advantage of this method is that there are easy formulas and tables available for quick calculations. You can look up normal distribution related tables on the web very easily and then use that as long as you know what you're doing. It can be plugged into a lot of formulas. Further, even from a statistical angle, a lot of distributions converge to being just like normal with a lot of, as the data size increases. So if you have a lot of data, many distributions kind of begin to take on the properties of a normal distribution. And so it's easy to hide behind that and simply say, yeah, I have a lot of data and therefore I'll just use normal distribution. Now, whether you really have a lot of data or not, obviously needs to be questioned. And then there's the symmetry. So what exactly do I mean by that? Well, the normal distribution, as you can see in the picture on the right-hand side, shows most data clustered around a stable average. And it has it's the maximum number of observations are close to the average, and then as you go further out, it becomes fewer and fewer observations. And that clustering in that shape where it's clustered around a stable average appears to be fair, appears to be predictable, and most human beings, fairness is something that we like. And so this is at some deep level, it evaluates as a quote unquote good distribution to consider. Also, it's very symmetrical, and symmetry is pleasing to the human eye, whether it's in phases, arts, or statistics or distribution. And as far as statisticians are concerned, they also like the symmetry because the mean and the mode and the median are all the same. And so the one half of the image or distribution is the mirror image of the other half. And that is also makes life easy when you're dealing with it in terms of the statistics and the underlying calculation. So these arguments, by the way, I picked up from an article from Harvard Business Review, but I think these are good reasons why the underlying symmetry appeals to people. All right, so we have reasons why it's popular. And by the way, the reasons that I just said, I said them in general sense, but it also applies on the demand sense, that being it centered around the average is appealing to most planners. But there's enough research that has been done that suggests not all demand data is normally distributed. So how do we go about calculating the safety stocks without making this assumption? So I'm going to cover three areas. I'm going to talk about the Poisson distribution. Going to talk about a method that I call scanning, and then I'll jump into bootstrap sampling. All right, so let's begin with Poisson distribution. The Poisson distribution is a discrete probability distribution that simply means that the underlying variable takes values, discrete values, so 0, 1, 2, 3, as opposed to, for example, continuous distribution would be like it will include things like 1.2 and 1.25 and 1.257, for example. And so the Poisson distribution gives us a probability of a given number of events occurring in a fixed interval of time if these events occur with a known constant mean rate. So the rate itself is not going up or going down, and independently of the time since the last event. Now, this is a definition. It's a mouthful. I picked it up from Wikipedia. If we kind of break it down a little bit to say, when is Poisson distribution appropriate? Well, here are some conditions. So first of all, if we have an event and we try to count it, and so the K is the average number of times an event occurs. Event can be anything. Event can be how many people come to a particular meeting room, how many messages you get in your chat box. These are all events. So K is the average number of times an event occurs in an interval of time, and K can take discrete values, so 0, 1, 2. That's a key requirement. Then the second requirement is that the occurrence of one event does not affect the probability that a second event will occur. So if we go back to the example of chat messages on whatever messaging technology you use, well, the fact that you got a message from one friend does not have any impact on getting a message from another friend. So these are independent events, and that's a key requirement in Poisson distribution. Then the other thing is that the average rate at which events occur is independent of any occurrences. So this simply means that in the time frame that we are considering, the average rate is a constant. Of course, in practice, this may vary with time. You may get more messages in the evening versus in the morning, but within the time frame of consideration, it's assumed to be constant. And the last thing is, two events cannot occur at exactly the same instant. So it is what we are saying is that there is a small gap. It can be a very small gap. It can be minute for all we care, but two events always have a little bit of gap, maybe 1 second, maybe 1 millisecond, maybe 1 microsecond. So if all these conditions are true, then we can say that K, which is, again, remember the count of number of times an event is occurring, then that K is a Poisson random variable, and the distribution of K is a Poisson distribution. Now, if all of that is not really interesting you, let's look at an example. So let's say you work in an office on a city block, and every day you hear some fire trucks go by, as it happens in big cities. So you can hear the fire trucks go by, their sirens going, and so now the question, it's just something that maybe it bugs you, or maybe you are just statistically oriented and you want to come up with a formula or kind of evaluate how many times these fire trucks are going by your office building. So you have looked at this data, and let's say you have figured out that on average, 2 fire trucks go by your office building every day. So now if we just quickly go through our list of criteria, we can say, yeah, every fire is independent of every other fire. So, one fire truck going by is not really going to impact the other one. The rate, well, given the city is the same, the rate of fire should be reasonably constant. Certainly, fire trucks are discrete. You will have either a 0 or a 1 or a 2. You will never have 2.5 fire trucks go by. So all of that suggests that this might be, the Poisson model might be appropriate here. And this data might be distributed in a Poisson distribution. So once we pass that hurdle, then let's say we are interested in evaluating the probability that on a given day, we will see 0 trucks, 0 fire trucks, or 1 fire truck, or 2 or 3 or 4 or 5. So like everything else, Poisson distribution has an essential formula. The formula is that for us to see or hear, as the case might be, k fire trucks go by, k being the count, it can be 0 or 1 or 2 or 3 or 4 or 5. The formula is E, which is the constant. Hopefully some of you will remember that from your math class. So E raised to the power of minus lambda. The lambda is nothing but that average that we talked about up there on the slide, which is 2, multiplied by lambda itself raised to the power of k. K is the value for which we are seeking the probability, divided by k factorial. K factorial is a mathematical construct. It simply means if you take a number 3, the k 3 factorial will be 1 times 2 times 3. If you take the number 5, then the factorial 5 factorial would be 1 times 2 times 3 times 4 times 5. So with that said, we want to ask the question, hey, what are the expected probabilities if we consider the question of k taking different values? So will we see 0 trucks, 0 truck, 1 truck, 2 trucks, 3, 4, 5, all the way up to 10? And so what I want to do is maybe just to see how you think about it, let's have a poll question here. Given the average number of fire trucks per day is 2, so that's a given that we started with, that we know the average is 2. How do you think the probability will work out? Will it be the lowest for 0 fire trucks and maximum for 10? Will it be highest for 0 fire trucks and minimum for 10? So will it be increasing? Will it be decreasing? And the third option, will it increase from 0 to 2 and then, I guess, decline? All right, so you have about half of you voted. Maybe the question itself was not so clear, so half of you decided not to vote. But for those who voted, 67% said that it'll increase from 0 to 2 and then decline. So let's actually do the math and see how it works out. So if I may come to the next slide, I pulled up a table where I have crunched the numbers in Excel, as one does in planning circles. So here we have the values of k, 0 to 10. The lambda, as I said, is 2. Then e raised to minus lambda. So in the first, actually in all of these rows, that e is a constant. So, and lambda is given 2. So these numbers are exactly the same. Then lambda raised to k, k being these numbers. So anything raised to 0 is 1. And then lambda raised to 1 would be 2, raised to 2 would be 4, and so on. So we calculate that. K factorial starts, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2. So as you can see, it grows very fast. And then finally, we put all that together. So e raised to the power minus lambda times lambda raised to the power k divided by k factorial. What we get are these numbers. So the probability of 0 trucks is 13%. Based on this formula. So 13, if you said, what are the chances that today I will not hear a single fire truck go by? Given the input, the probability works out to 13.5%. The probability of exactly 1 truck passing by is 27%, which matches the probability of seeing or hearing exactly 2 trucks go by. So that's also 27%. And then from there, it begins to decline. So all of you who voted for the third option in the poll, you were right. It begins to decline. The odds of us hearing 3 trucks are 18%, 4 trucks are 9%, 5 trucks 3%, and so on. And by the time you are at 7 or 8 or 7 trucks, basically for all intents and purposes, the probability is 0%. So really there's very small chance that you will hear more than 6 trucks go by. So that is the essential math behind Poisson distribution as it pertains to the distribution itself. Now, this is nothing to do with safety stock. So we need to still think about converting this to safety stock. So let's take an example where this might apply. So many of you might be in businesses where you sell spare parts. The spare parts obviously are connected to the original equipment that was sold, machinery, and without the spare parts, those machines will break down eventually. So the spare parts are necessary to ensure operations. However, the demand for the spare part happens in a very erratic fashion, sometimes can be lumpy, and certainly for sure it's slow moving. You may sell 1 or 2 or 5 units in a year. So if you do that, the assumption of normal distribution, which relies on a lot of data, for example, would be bad, and it may lead to higher costs than intended or than needed. On the other hand, the Poisson distribution might be a good fit because we are always selling the spare parts in discrete quantities. We are selling them in small quantities, and we are selling them in an erratic kind of fashion. And certainly one machine breaking at one place may have no correlation with another machine breaking another place. So every demand instance is independent of each other. So this fits the bill of using Poisson distribution to calculate the safety stock. So now the question is, how do we calculate it? So what we want to say is, let's say we have a service level P. We need to choose the overall stock level S such that the demand D is less than the stock S with a probability of P. If the demand D is less than S, we will not have a stock out. If we do not have a stock out, that means we are doing a good job of meeting the demand. So the question is, up to a certain percentage of the time, we want to make sure that demand is less than what we stock. So if the demand is Poisson distributed in a Poisson fashion, then we can apply the formulas. So if we assume that the demand D is a Poisson distribution with an average or mean of lambda, then we want to find the stock such that the probability of demand more than that stock is greater than or equal to P, P being the service level. So when we think of it like that, in other words, we are not interested in, going back to the fire truck example, we are not interested in whether it's 1 truck or 2 trucks or 3 trucks. We are interested in the probability that it is less than or equal to 2 trucks or less than or equal to 3 trucks. So if we do that, the P probability of demand less than or equal to what we stock becomes a cumulative calculation. So we want to accumulate the calculations from 0 all the way to S of the same Poisson distribution formula that we had on the other screen. So let's look at this through an example. So let's say we have a particular spare part. The demand during lead time is exactly 1 unit, and the desired service level is 95%. How much safety stock should one carry? Well, if you plug it into the very similar, table very similar to the first one, we can see the numbers, and the only difference between this table and the previous table is this last column where we have done some cumulative. So you can see that, for example, the second row is the sum of the first 2 rows, and the third row is the sum of the first 3 rows, and so on. So what we see is, if I carry 0 inventory, there is 36% chance that my demand will be 0 or less, and therefore no trouble. But there is 64% chance that the demand will be more than 0, and therefore I will have a stock out. If I carry 1 unit, I'll have 73% chances that my demand will be 1 unit or less, and then therefore 27% of the time it will be more than 1 unit, and I'll have a stock out. So if you keep going down that way, when we reach 3, if we are going to keep 3 units of inventory in safety stock, there's a 98% chance that my demand will be less than 3 units. So since my target service is 95%, when I have 2 units, I'm only at 91%, and when I have 3 units, I'm at 98%. So that's where we have crossed the 95% threshold. Well, that's how much safety stock I should carry. If we change the numbers a little bit, we say, what if the average was 2 units? Well, guess what? The numbers move, and I actually need 5 units in stock to achieve that 95% service. You could certainly say 4 units is probably close enough as well, because that gives you 94.7% service. But if you really wanted to be on the other side of 95%, then you need 5 units. If you similarly do the calculations for 3 units, so see the average demand is 3 units, well, then you need 6 units of product in stock, spare part in stock, to get to the 95% service level. So one can certainly, once you have the Excel sheet handy, change the lambda. Everything can be very easily calculated. What is important to understand is that as the average itself moves, the probability distribution that we calculate using the Poisson distribution actually begins to take a very recognizable shape. So you can see if when the lambda is 1, it's this blue curve. When lambda is 2, it's this light green curve. Lambda is 3, it's dark green, and so on. But look at this lambda equal to 5. Doesn't it look very similar to a normal, the shape of a normal distribution? And certainly by the time we are at lambda equal to 10, it's very much like a normal distribution. So higher values of lambda begin to resemble normal distribution. And so if you have a spare part that sells a whole lot, well, in that case, you don't have to always go towards Poisson just because it's a spare part. You know, if the lambda is large, you can go back to the normal distribution assumption, for example. So just summarizing, Poisson distribution is discrete probability distribution. It has a single parameter called lambda, which is just the average. That parameter is both the mean and the variance. Like the normal distribution, sums of Poisson are also Poisson. And important to remember, Poisson distribution becomes approximately normal when the value of lambda is large. All right, so that's one case, and hopefully you can put it to use in your business. And in that, we did not use the assumption of normal distribution. So now we'll move on to the other two parts, the scanning and bootstrap sampling. And so here we are considering a time series. For folks who have watched the first two webinars, this will look like what I use there because it's exactly the same data series. So here is some demand. Some days we sell 1 unit, 2 units, some days we sell 4 units, and so on. The daily average is 1.46. The daily standard deviation is 1.70. The average over lead time, which is 7 days, is 1.46 times 7, so that gets us to 10.24. And the standard deviation over lead time is 1.70 times square root of 7, and that gets us to 4.50. All right, so the first method we'll discuss is scanning. And so the idea here is that we draw a box around the demand data. The box has a width equal to the lead time. So in this example, the lead time is 7 days. So this box is 7 days wide. And we sum up the demand inside that box. So that is 1 plus 0 plus 2 plus 4 plus 1 plus 0 plus 0, and we get to 8 units. Then we slide the box by 1 day, and we do the same math, and that gets us 9 units. Then we slide it again by a day, and again we add the numbers, and that gets us 9 units. And then we may do it one more time, and that gets us 7 units. So since in this example, I have 54 days of data, I can draw 54 minus 6. So that would be 48 individual boxes. And then in each box, I can calculate the sum and figure out where the maximum demand is inside any of these boxes. So if that actually happens to be twice in this data set, so twice we have a demand of 17 units in that data. So that we call as demand during the lead time, which is the demand inside the box, and the max value of demand during lead time is 17 units. So one way of calculating safety stock using a 95% service level would be simply to multiply this 17 number, which is the max demand in any 7-day bucket, with 95%. We get to 16.15. The average of that, the 7-day demand is 10.17, which will be covered by the cycle stock. The safety stock would be 16.15 minus 10.17, which gives us 5.98 units. That's easy enough. Some may actually do the math slightly differently. They may actually apply the 95% before they do the summing, which is fine. It'll not really change the math. The sum now in every individual 7-day box, the maximum you will get is equal to 16.15, which is nothing but 95% of the previously calculated 17. And the safety stock will come to exactly the same number, 5.98 units. So this is the method that I call scanning. I'm not aware of a more formal name for it. And you can do more variations on it. You can do the calculation based on percentile. So if you use the percentile formula in Excel, the idea of percentile is what is the data point below or above which 95% of the values lie. In this case, we are interested in below. So the 95th percentile point for this data set is 14. Since we already know the average is 10.17, the safety stock will be equal to 14 minus 10.17, which is 3.83 units. So scanning is kind of a rule of thumb method, and you can tweak it to your own liking or based on whatever you are used to. You can also, since we have the data, calculate the safety stock using the assumption of a normal distribution. So if we did that, the Z factor for 95% is 1.64. The safety stock then is 1.64 times sigma DDLT. Sigma DDLT is the standard deviation of demand during lead time. Again, we discussed this in great detail in part 1 and part 2. So the safety stock becomes 1.64 times 4.50, and that gets us a value of 7.40, which you will hopefully notice that it was bigger than the 5.98 that we calculated earlier. So if we compare the safety stocks that we calculate using the scanning method versus the assumption of normal distribution, we see that safety stock from scanning method is 5.98. Safety stock from assumption of normal distribution is 7.40. As a percentage, 5.98 is 80% of 7.40. Now we can also back calculate the Z value for the scanning method. If we take the 5.98 and divide it by the standard deviation, which is 4.50, we get 1.32. So that's the Z value. Remember, for 95%, the Z value was 1.64. So this is obviously less than 1.64. We can also look up the tables on normal distribution and back calculate the service level. So the service level for a value of 1.32, for the Z value of 1.32, excuse me, is 90.5%. So if the data is normally distributed, then the scanning method is giving us a safety stock that is only giving us 90% of service. On the other hand, if the data is not at all normally distributed, then this comparison is kind of bogus. So you can do a lot of these types of calculations using the scanning method. So scanning method, like I said, is a rule of thumb kind of method. It's common sense kind of method, and it has its own drawbacks. You can get to too little or sometimes too much safety stock. You can have, therefore, too low or too high a service level. Given that it's not a statistical based method, some people will immediately reject it, whereas some other people might love it for its simplicity because they can easily replicate the formula in Excel. My suggestion is that just because it's rule of thumb does not make it bad right out of the box. However, it does have one challenge in that it is relying on a sequence of observed demand. So when we draw that box, the box is around 7 consecutive days. Now, one big assumption in safety stock theory is that demand on each day, in each period, I should say, is independent of demand on the subsequent or the previous day. So when we draw these boxes around 7 consecutive days, we are kind of saying that the sequence matters, that what happens on day 2 and day 3 and day 4, they go together. And that is maybe one big reason why I might say, you know what, be careful in how much you use the scanning method. But in the absence of anything else, it's not a bad way of calculating the safety stock. All right, so we have covered 2 of the areas. Now we get into bootstrap sampling. This is something that I actually very briefly touched on in the previous webinar, but I got suggestions that I should show this in a more how-to format so that people can actually replicate that in their business. So here it is. So bootstrap sampling. First of all, the word sampling suggests that if we have some data, we are going to sample We are going to pull out some data from it. And the peculiar way the bootstrap sampling does it is that if we have n number of data points, in this example, n equal to 7, we have 7 data points, then each of our samples should have exactly 7 data points in it. And the sampling itself is done with replacement. That means that as soon as I draw something out as a sample, I note it down and then I put it back in the bag so that potentially I could draw it again. That is called sampling with replacement. So Bootstrap, one requirement is that each sample must have exactly the same number of data points, and 2, that we have to do the sampling with replacement. So let's see what it looks like. So let's draw our first sample. And so our first sample out of these 7 names is James. So we pulled it out here, but because we do the sampling with replacement, notice that James is still there in the original box, which means if I go and sample again, I close my eyes and sample again, pull one more name from the box, it is possible that I may get James again. So let's do that. Well, the second sample that I get, second entry is Abby, so that's good. Well, when I do the third sample, I get James again. That's the replacement in play. And then I get Mike. Then I get James again. So James has been now sampled 3 times in this sample. Then Mike again. So Mike is going a second time. And then Sandy. So as you can see, now my sample is complete. It has got exactly 7 things selected in my sample. But I have selected James 3 times just out of random luck. And I've selected Mike twice. Abby and Sandy have been selected only once. And John and Max and Joe were not selected even once in this sampling. So if you do this, and certainly since we are doing it with replacement, it allows us to do the sample any number of times. I can draw 1 million samples out of these 7 data points if I so wanted. So basically the idea of bootstrap sampling is to draw the sample enough number of times that you have a good statistical basis to draw some logical conclusion. So maybe 100 times, maybe 500 times, maybe 1,000 times, depending on how much computing power you have and so on. So that's the explanation of the sampling. Let's look at it with actual sales data in Excel. So because we are ultimately not interested in names, we are interested in using this technique to calculate safety stocks. So I'm going to flip into Microsoft Excel, and I'm going to show you some data. Now this data on the left is exactly the same data that I showed you in the graph. So basically I have 54 days of data. If I scroll down, this goes all the way to 54 days. And then I have the actual sales data that happened on that day. So on day 1, I sold 1 unit. On day 2, I sold 0 units and so on. So think of the day column as the address of the data, and then think of the actual column as the actual data. So now what we are interested in is we are interested in doing something called a random sampling. So I'm going to actually show you how I do that. So there's a command in Excel called rand between, which is short for random number between 2 values. So I've put a formula here which says, and I know we are dealing with people who are into supply chain planning, so I know that you guys are experts in Excel more so than me, but if you bear with me, it's saying pick a number which is a random number between these 2 values, between the values of 1 and 54, because I have 54 data points, so I have individual addresses for each of those data points, and I just want to pick one of them. So if I do that, notice that the very first row, the number is 52. And right next to it is another formula that says, based on whatever is selected as the address, go to this list and match the observation. So if we go to day 52, if I just scroll down to day 52, well, lo and behold, I did sell 1 unit on day 52. So here, all it's doing is it's pulling out that as the data. So this here, the rand between formula is generating for me a random address from where to pull the data. And then this here is simply pulling that data. So if you look at second entry, the random number is 4. Well, on day 4, we had sold 4 units of data, 4 units of demand, and therefore we get the value of 4. On day 17, which is here, I had 0 units of demand. That's exactly what I see. So this rand between command, if you are using Excel to do this, is a clever way to do this random sampling. Now, because I have a lead time of 7 days and I want to replicate these random sampling for a 7-day period, I'm going to pull 7 unique samples. So I have this sample here, which I'm calling sample 1. Then this sample here, which uses the exact same technique, and I get sample 2. Then I have sample 3, sample 4, sample 5, 6, and 7. And all of that is basically going to the original data and doing a sampling with replacement. And all of them have exactly the same number of data points as in the original data, which is 54. Once I've done that, I can sum those observations. So now, since I have a sample 1, a sample 2, a sample 3, and so on, over here, I've simply added those up. So now for every cell, I'm adding it up. Now, I don't know if you noted, but as soon as I clicked out, the numbers changed. Why is that? Because in Excel, anytime you use the rand, anything to do with random numbers, in this case, this rand between has the random number behind it. Anytime I change something, it will redo the random number drawing. So this will keep changing. And so these sums themselves will also keep changing. So if I take that sum and go all the way to the bottom, I can calculate the average demand during lead time. Notice that this is already a sum of the 7 days. So I can then average those numbers, and I get an average demand during lead time based on these 54 observations. Then I can calculate a 95th percentile demand during lead time. So my question when I do that, by the way, that's the formula in Excel, percentile. And so the point I'm interested in is, where is the point below which the data observations are 95%? So in this 54 unique observations of the sum, the 18 is the number below which 95% of observations lie, and above 18, 5% of the observations will lie. And so then the safety stock calculation is a very simple 95th percentile number minus the average number. If you think about the normal distribution, the average number is the middle of the normal distribution, and the 95th percentile is where that z value becomes 1.64. So here, the thinking is similar, but we are nowhere invoking the normal distribution. We are actually using a very data-driven 95th percentile. When we go by percentile, we are not imagining, or we are not forcing any distribution whatsoever. So we get the value of 7.26. Now, if I copy these numbers and I paste them in Excel as values instead of as formulas, I can do that. As soon as I do that, guess what? Because this is a random number generator, Excel will refresh the calculation for me. So notice that everything will change. So I do the paste, and these numbers have already changed. And if I copy this, if I paste the formula, paste the values rather, it'll keep changing. So I can get 100 times or 500 times or 5,000 times, I can calculate these safety stocks. So that's what I've done down here. I've copy pasted it exactly 100 times. And after that, I got tired, I suppose. So here you can see that I have copy pasted the average, the 95 percentile, and the calculated safety stock exactly 100 times. And then I've taken the average of those numbers. So the average of the average demand during lead time calculates to 10.15. Average of 95th percentile DDLT comes to 17.63, and the average safety stock comes to 7.48. So now, with all these calculations, I'm ready to say that I'm pretty comfortable with a safety stock of 7.48. And notice that I've made no assumptions about normal distribution. So that's what the idea of bootstrap sampling is. And now I've actually shown it to you in Excel. So hopefully you can replicate it in your own world. So in this example, 100 bootstrap samples, each consisting of 7 randomly generated days. We get the average of average DDLT as 10.15. Remember that the original data had the average of 10.24, so it's reasonably close. The average of 95th percentile DDLT is 17.63, which gives us a safety stock of 7.48. Now, it just so happens that this is actually 101% of the safety stock that we calculated from the assumption of normal distribution, which was 7.40. So it's actually quite close. And then it is 125% of safety stock that we calculated from scanning method. So the reason it's very close to normal distribution, it simply could be that simply could be luck, but it also could be that this particular data set is very close to normally distributed, and our bootstrap sampling is getting us very close to that. In fact, if you generate raw data, again, you can do this in Excel as well. If you generate raw data that is normally distributed, and if you take enough bootstrap samples out of it, you will find that your bootstrap samples will also show a tendency to be normally distributed. So, all right. So what we have shown here is an approach which you can implement using Excel. And certainly if you have access to some programming methodologies, then you can do it in a more robust way in using code. Now, this is a very robust data-driven approach. It is not assuming any distribution whatsoever. So certainly the underlying math is not all that difficult. I mean, it's just a question of sampling, and you can certainly do it in Excel, but you can also do it in automate it using some code, whether it's Python or C# or whatever. And then ultimately we are calculating the safety stock based on a percentile and not based on any distribution and any z-value and so on. That's the approach. I think it's a very robust approach. It can apply to really any data. As long as you have enough data, you can apply this approach. Just keep in mind that you have to draw, the sample should have the same number of observations as you had in the original data set, and remember to do the sampling with replacement. All right, so that's kind of what I wanted to talk about in this third and final part of the webinar series on safety stocks. So let's conclude. When you're dealing with very small and erratic numbers, consider the Poisson distribution. And whenever you are in doubt about whether or not normal or Poisson or any distribution applies, you can certainly consider bootstrap sampling, which is a very robust data-driven approach and does not assume any distribution whatsoever. And at the end of that, you will achieve more robust results without falling into the trap of underlying assumptions. So that's the webinar. We do write about these and other related topics on our blog. So the QR code on the top allows you to take a look at that blog. But that's my presentation, and at this time I will turn it over to Kristen.
Great, thank you, Sujit. That was really informative and I hope very useful for the people that were able to join us today. If you would like a personalized product demonstration on how Arqiva can help you achieve a better planning process and specifically calculate safety stock, visit our website at www.arqiva.com and click the Get a Demo button in the top right corner. We will now move into the Q&A portion of our webinar. We do have a couple questions that have come in, so I will start with those. And as a reminder, you can submit an online question using the questions window in the GoToWebinar console. Okay, let's see. We have a business where we ship in trucks. The quantities themselves are not discrete, but the truck counts are discrete and very small. Can we apply Poisson distribution there?
Well, the quantities are small, they are discrete, and I imagine a truck going out today has no impact on the truck going out 3 days or 7 days or 15 days from now. So yeah, at a high level, it does sound like you can use Poisson distribution. Of course, then the answer that you will get, just keep in mind, will be in values of trucks. So your answer would be, should we carry 1 unit of stock or 3 or 7? certainly you can from truck then back calculate it to the actual number of units, but the Poisson distribution, if you want to apply it, and does sound like it's applicable, will then should only be used to determine the number of trucks and not the underlying units, because that presumably is not discrete and certainly is not distributed as a Poisson distribution.
Okay, great. Another one is, can bootstrap sampling be applied to items that are very low in volume?
Yes, as I was saying earlier, the only thing, the bootstrap sampling has the two requirements, right? That each sample must have the same number of observations as the original data, and the sampling itself must be done with replacement, which means that the same data point can be pulled out 2, 3, 4, 5 times. Once you do that, and if you are very robust in your approach, by that I mean that instead of just drawing 1 or 2 samples, you're drawing 500 samples, which will really give a level of robustness to your sampling, then I think that there is nothing that prevents it to be used on small volume or sporadic items. So in other words, if you don't want to go to the Poisson distribution at all, you simply want to use bootstrap sampling on spare parts, you can do that. And that should give you very comparable and very data-driven, robust results.
Okay, great. Let's see, we have another one that came in. This one says, some demand planners have suggested that we should ignore the usage data during the downturn that followed the COVID pandemic. I'd prefer to keep using as much data as we can. How can we decide whether it is a good idea to ignore historical data?
I think it's never a good idea to ignore any data. Now, what they are probably hinting at is that during the downturn, the data that you have is a little bit of an outlier. And so if it is an outlier, there are methodologies available to do some outlier correction. Also, we are at this time 2 years removed from COVID, at least if my math is right, or yeah, it seems like it's been a while. And so if you're calculating safety stock, you don't need to look, unlike statistical forecasting, you don't need to look 3 years, 5 years back. You probably want to look no more than 12 months back. And so in that sense, the COVID data in general should not have any impact whatsoever. Having said that, if we turn this into a more general question, I think if there's a downturn, there's a good question to be asked. Should we treat this as an outlier or not? And if you decide to treat it as an outlier, then you may have to do some outlier correction before you calculate the safety stocks.
Okay, great. It looks like that's all that has come in. So if anyone has any additional questions, feel free to send them over to us after the webinar, and we'd be happy to get responses out to you for those. So that is the end of our session today, and we hope that you will join us for our next live webinar, which will be how to build the ROI case for demand inventory and supply planning software implementation. More information and registration will be available soon for that session. And as a reminder, please take a few minutes to answer the short survey at the end of the webinar. Thank you again for joining us today, and we hope you have a great rest of the week.